All right, so we're in chapter 7 now, this first section of chapter 7, 7.1, we're actually not going to be looking at any differential equations. We won't start that until towards the end of 7.2. What we're doing here is we're developing a technique that's going to help us solve a number of differential equations using something called the Laplace transform. Now, the Laplace transform is an example of what we call an integral transform, and we'll give its definition in just a second, but the idea behind an integral transform is that we are basically creating a function that involves an integral of some kind. As its input, it takes some function of one particular variable. In our case, that variable is going to be t. And then in that integral will be another unknown s. And for the purpose of integration, we think of that s as a constant. But then when we integrate the function, the t, the variable t, kind of integrates out and is replaced by this unknown s. So essentially what an integral transform does is it takes a function of some variable, say t, and takes that as an input, and then its output is a function of some other variable, s. And it's going to be, like I said, it's going to take us until the end of section 7.2 before we see how this is useful for differential equations. Right now, we just need to start getting some familiarity with it. So here's our definition of the Laplace transform. Suppose, first of all, that we have some function f of t, and it's defined for all non-negative values of t. So t is going to be greater than or equal to 0, and what we're going to do is define this function called the Laplace transform, and it's important to understand that technically the Laplace transform is a function, but its input is not a real number, it's not a complex number, its inputs are functions. So it's a function that takes other functions as inputs and provides functions as outputs. So the notation that we're going to use is this kind of script capital L, and technically this L is not the one that you're going to see in the textbook. Let me jump ahead a little bit just so I can show you what the L is supposed to look like. Here's what the L is supposed to look like. It's a little bit more cursive-y, if that's a word. We'll get to that page later, but I couldn't find that font on my computer. So this is what it's going to look like when I have typed it. But anyways, it's this capital L of f of t, and what it does is it integrates this function, e to the negative st times f of t dt, and the integral goes from 0 to infinity. So it's a definite integral, and it's defined because, again, f of t, we said, is defined on that interval from 0 to infinity. That's what this is saying. Any exponential function we know is defined everywhere, so this is well defined, it's valid. But think about what would happen when you integrate when you find the definite integral of a function. Generally, what you get from that is a real number, right? So the function t doesn't show up again after doing the integration and evaluating it at these limits of integration. So when we integrate this guy, the t's will eventually go away, but that s, because it's unknown, will be sticking around in some form or another. So the end result of this thing will be a function of s. And that's kind of the basic idea behind what we're doing here. So we're taking functions f of t, plugging them into this integral transform, this thing, and out pops another function of s. Provided, of course, that this this integral is defined. Remember, this is an improper integral because it's going from 0 to infinity, and it's possible that for some functions f of t, that this will not converge. This may go to infinity or negative infinity. It may end up being something that's undefined. So we have to be careful to take that into consideration. A little bit later, we'll look at how to determine whether a function will have a Laplace transform, a finite Laplace transform, or not. But let's jump into some examples. Now, I'm going to preface this by saying that in most of the lectures that I do, even though I kind of follow the basic structure of the sections in the book, typically I try to pick different examples than are appearing in the book itself, just to give you something else to go on if you're reading through the book as well. In this section, I'm going to be doing a lot of the same examples that the book does, and there's a specific reason for that. We're going to be evaluating a few Laplace transforms of very important functions. And from these functions, using the linearity property, which we'll talk about, we'll be able to build up Laplace transforms of other functions. So the ones that we're talking about here, they show up as examples in the book, but we need to talk about them. And we need to do these examples. So that's why if you're following along in the book and you see this exact example showing up first, it's important that we do it, okay? So here we're being asked to find the Laplace transform of the constant function 1. Remember, we think of this as a function. So the notation that we actually want to use is that, okay? How do we define this? Well, according to our definition, this is the improper integral. It goes from 0 to infinity of e to the negative st times 1 dt. 1 is my function f of t. Now remember, when you're dealing with improper integrals, technically we define these as limits, right? So to be a little bit more careful, I want to make sure that I'm thinking of this as a limit. I'm going to say as b goes to infinity, and I'm going to replace my upper limit of integration with b, e to the negative st. I know that that 1 doesn't need to actually be written anymore, so I'm just going to do that, okay? So now I'm going to perform this integration. This is a really easy integral to do, but we need to remember that s is being treated like a constant here. T is the variable. So that means that we're evaluating this. Okay? So this is going to look like e to the negative st over, let's say, negative s, like that, and it's going to go from 0 to b. Okay, well, what is that equal to? That's equal to the limit as b goes to infinity of, let's pull the negative 1 over s out, negative 1 over s. I'll pull that out there. Remember, that's a constant. We can do that. Negative e to the, sorry, that's positive now. I pulled the negative out. E to the negative sb minus, when I plug a 0 in for t here, that's going to equal 1 over s. I brought the s out, so that's just 1, or negative 1 over s. Okay, now at this point, we want to evaluate this limit, but we have to be really, really careful because depending on what s is, the limit as b goes to infinity might be defined, it might not be defined. So for example, if s is a negative number, then minus s will make that a positive number. B is going towards infinity, so we think of that as a very, very large positive number. So that means this exponent, in the case where s is negative, is becoming larger and larger in the positive direction, sending this exponential function off to infinity. In that case, the limit, we would say, is not defined. So this limit does not work when s is negative. But what if s is greater than or even equal to 0? What happens in that case? Well, actually, sorry, if e is equal, if s is equal to 0, then this is equal to 1, and we have 1 minus 1, the whole thing goes to 0. But if s is positive, what can we say about this limit here? Well, if s is positive, then minus s would be negative. B going to infinity is going to take this entire exponent towards negative infinity, which shrinks this term down to 0. And that means this expression in here is going towards negative 1. Multiply that to negative 1 over s, and we get positive 1 over s. And again, remember, this only worked when s was positive. Okay? So we need to, when we're doing a Laplace transforms, there's always a step in there where we have to take this into consideration, where we have to think, okay, because there's a limit involved, but we don't know s, that limit can either be defined or not defined depending on what s is. And so we have to determine for what values of s will that limit be defined, and then what will it look like in terms of s, okay? So this is the Laplace transform that we were looking for. All right. Now I'm going to do something just for notational convenience for the rest of the examples. Even though this limit is involved the entire time, I'm not going to be writing that limit every time. In fact, what I'm going to be doing is jumping straight from this step to this step, but instead of writing limit as b goes to infinity, I'm going to remove that limit and just keep an infinity here. And what that's going to do is, in the back of our minds, we're interpreting that as a limit. We're not actually thinking of that as plugging infinity into something. Let's try another one, another really important function. Again, this shows up in your book, the Laplace transform of the function t. You know, f of t equals t. What does that look like? Okay, well, we're going to go like this. Laplace transform of t, and that equals the integral from 0 to infinity of e to the negative st times this function t. I'm going to put the t first, e to the negative st, just because I like the way that looks better. Okay, this is a classic integration by parts problem, right? So typically you would say let u equal t and dv equal e to the negative st, so that du is equal to dt and v is equal to include the ds or dt in there, e to the negative st over s, and this is negative. Okay, I'm not going to write this every single time necessarily for doing integration by parts, but you know how this works. Okay, so using integration by parts, then this should come out to uv, which I can write as negative t e to the negative st over s from 0 to infinity. And again, remember, this would normally be involving a limit here, but we're using a notational thing here. This makes this more convenient. Plus the integral v du from 0 to infinity. Notice the v has this 1 over s here, which is again being treated as a constant, so you can technically take that out, take the negative out with it, and it'll change the minus that's supposed to be here to a plus. So that's actually going to be plus 1 over s from 0 to infinity e to the negative st dt. Okay, now I want to point something out here, because if we can evaluate this integral pretty easily, there's no, it's not a challenging integral to do, but bear in mind that we already did that. Remember, this integral right here is this integral. It's the Laplace transform of the function 1. So really, I can just use my previous work to get an answer to this. First of all, one thing I want to point out again is that we have to think of this as a limit, and we have to think of what values of s would cause this limit to be defined, and what values would cause it to be undefined. And by the same logic as the previous example, s needs to be positive in order for this term to shrink to 0 as t goes to infinity. If s is negative, then the whole thing blows up technically to negative infinity as t goes to infinity. Or actually, it would go to positive infinity, because this would be negative as well. But the point is that for the same reasoning as before, s will need to be positive in order for this limit to be defined. And in that case, the limit as t goes to infinity will shrink this to 0. And then, let's see. Sorry, no, that's incorrect. So as we would use something like, I'm trying to think of it. Why can't I think of the name of it? L'Hopital's rule, that's what it was. This whole thing will shrink to 0 as we evaluate both of these limits of integration. So we're left with this integral right here, 1 over s. But remember, this integral we defined, or we evaluated in the previous example, it was the same thing as the Laplace transform at 1. And we are paying attention to where this thing will be defined. It's when s is greater than 0. We've already evaluated this. We found that this was equal to 1 over s. And so this comes out to 1 over s squared, where, again, s is positive. Okay? So, kind of moving forward with this, a natural next function we might want to try is this guy, the Laplace transform of t to the n, where n is any positive integer. Now, because we're evaluating this for all positive integers of n, that's implying that there's some sort of formula or some sort of trick that's going to, or not a trick, but a formula is a better word, that we can plug n into and get the Laplace transform for any value of n. Now, if you notice, we've already evaluated one of these when n equals 1, because that was our previous example, right? So this is a classic proof by induction kind of thing. And if you haven't done induction in a long time, or if you, for some reason, never learned induction, we usually cover it in like pre-calculus. That's okay. Try to follow along. I'm not going to ask you to reproduce any proofs by induction in this class. But basically, when you do proof by induction, you have what's called the base case. And what that means is we're trying to prove the result that we're looking for the smallest value of n, which in this case would be 1. If n is a positive integer, that's 1. And we've already done that. There's nothing more to prove here. The Laplace transform of 1 we found was equal to 1 over s when s is positive. Now what we need in order to do the next step is called the inductive step. And the idea behind the inductive step, again, if it's been a while since you've done a proof by induction, you assume that whatever result it is you're trying to prove is true for some positive integer n. We've already established one possible value of n for which it's true. But then you make it a more general thing, and you say, let's suppose that the Laplace transform equals this formula that we're going to talk about in a second for some positive integer n. If that's the case, then that will imply, what we're going to show is that will imply that the formula also holds for n plus 1. And that creates this recursive formula of sorts that establishes the result for all positive integers n. So I'm going to jump ahead for a second because we have this table of Laplace transforms that we're working on right now. And you'll see the result that I'm talking about right here. According to this table, the result that we should be getting is that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1 factorial. And to verify that, for t to the first power, the one we already evaluated, that would become 1 factorial, which is 1 over s to the 1 plus 1 power, or 1 over s squared. And again, s needs to be positive for that to work. So that we've already established, we can see that that holds. But what I'm going to do is write that result off to the side or up above here, I think. Here's what we want to be true. N factorial over s to the n plus 1, where s is greater than 0. And so we're going to assume that. Assume the Laplace transform of t to the n equals n factorial s to the n plus 1, where s is greater than 0. And even though I'm not writing it, I'm saying that, well, I'll go ahead and write it. For some positive integer n. Okay? Now, what I want to do is evaluate the Laplace transform of t to the n plus 1. Okay? By definition, that's equal to the integral from 0 to infinity of t to the n plus 1 e to the negative s t dt. And again, we need integration by parts for this to work. So what would integration by parts look like? Let's figure that out. U is going to equal t to the n plus 1 in this example. dv will equal e to the negative st. v is going to equal, it's got a dt there, negative e to the negative st over s. du is going to equal, I didn't leave myself a ton of room, but n plus 1 times t to the n dt there. Okay, so making some substitutions, or not substitutions, but using this in the integration by parts formula, we're going to have the integral of uv. So again, this will look like t to the n plus 1, e to the negative st, let's put a negative here, s from 0 to infinity, and once again, you can show that this will go to 0. And then pull the negative 1 over s out, so this becomes negative 1 over s. integral from 0 to infinity, and now we have v du. So actually, let's pull the n plus 1 out with that as well. N plus 1. Okay, it's a little bit sloppy, but whatever. So I pulled the negative 1 over s out. I pulled this n plus 1 out. I'm going to be left with t to the n e to the negative st dt. Okay, and I have this little factor that I pulled out, and actually the minus will become a plus because I'm going to pull that negative out with it. So this guy goes to 0. This thing right here is the Laplace transform of t to the n. So this is equal to n plus 1 over s times the Laplace transform of t to the n, and this will be equal to n plus 1 over s times, since we've already made an assumption about what this is equal to right here, right there, this is equal to n factorial over s to the n plus 1. And of course, this is n plus 1 times n factorial is easily seen to be n plus 1 factorial over s to the, now if I multiply this, the natural thing to want to do is to write it as s to the n plus 2 power. I'm going to write it this way though, s to the n plus 1 plus 1. Now if you notice what this is the same thing that I would have gotten by plugging n plus 1 in to this formula right here. N plus 1 here, n plus 1 in for that n right there would generate this formula. And that's what it's supposed to do. That's verifying that the formula also works for n plus 1, where s is greater than 0. Okay, so that actually establishes the result that we're looking for. Normally you'd have a concluding statement here and a proof by induction. You'd say, by the principle or by the first principle of mathematical induction, such and such is true. I'm going to skip that just because all we want here is an answer, and I'll repeat my answer over here. T to the n equals n factorial over s to the n plus 1, where s is greater than 0. Okay, I'm going to do one more example on this first part, and then we'll start another video after that. Looking at another Laplace transform, the Laplace transform of e to the at. Okay, so for this guy, let's do what we've been doing. We'll set it up. Okay, this will be equal to the integral from 0 to infinity of e to the negative st times my function f of t, which is e to the at dt. And you should be able to see pretty easily that we can combine some stuff here. So this is equal to the integral from 0 to infinity of e to the, let's write it this way, negative s minus a t dt. Okay, now this one integrates really, really nicely. This is an easy one to do. So integrating this guy, we're going to get this negative e to the negative s minus a over s minus a from 0 to infinity. Okay, now here's the stage where you have to consider whether this is defined or not. I need this in parentheses here. So as we've kind of seen, we would like for the exponent on this e right here to be a negative number, because then when I evaluate this, which remember that's the limit as what we would be calling b goes to infinity, I forgot my t there, that's going to send this guy to 0. If this exponent here is not negative, then the limit's going to send this thing off to infinity, and we're not going to have a finite Laplace transform, which is what we want, or a defined Laplace transform. So what does it take for this coefficient on that t to be negative? Well, s minus a would have to be positive because there's a minus out in front. So this will be defined if s minus a is positive, okay? But that's the same thing as saying s is greater than a. So if that's the case, what happens when we evaluate this? Well, this will be equal to when I take the limit, it'll send this thing off to 0 minus this thing evaluated at 0. If I evaluate this at 0, this becomes negative 1 over s minus a. Minus negative 1 makes that positive 1 over s minus a. And this will be defined when s is greater than a. Okay? And again, I keep jumping back and forth, but notice that's what we have right here. Now, this table that came from your book, they don't include the restriction for some reason where it says s is greater than a, but you have to remember that that's part of our Laplace transform here. Okay, I'm going to go ahead and stop this video here, and we'll keep going in the next one.